I talk in the video?
Yeah. Hi, Pre-Calc. This is the Friday of Bros this week, or what would have been the Friday of Bros this week. So we're coming at you today with, I'm wearing a Bros shirt from past years. This one was from 2018, Fairport Family. It's not rare to care. Maybe some of you even have that shirt in your collection somewhere. But since we couldn't go visit our elementary buddies, I have a special guest here with me to start off the video. And let's see, can we sneak up our special guest here? Here she is. Say hi.
Hi.
And what did you make?
I made a special picture about math since you love math. And it says our names just because we both love math. And this picture shows us about some numbers.
Yeah, so let's see if we can zoom in a little bit. I don't know. Can you see it says I love math up at the top there?
Yeah.
And then it looks like we've got a whole list of numbers here, some hearts off to the side. We've got some great crafts happening over here. Even though we couldn't be together for Bros this week to meet our buddies, you know what? Well, hopefully if we get back to school, we'll be able to meet up at some point. So thanks for making me that picture.
Have a great day at high school.
Oh, that's awesome. They're going to have a great day, I think. Thanks so much. All right, you're going to go make some more pictures?
I'm not. I'm actually gonna write, I love Mr. Green.
Oh, okay, we're making a note for Mr. Green, the principal over at JA. So
I'm also gonna use the tape just because I'm gonna cut it out on another piece of
perfect. Sounds like a plan. Okay. So happy Bros this week, guys. It's a little bit different this year, of course, but what I actually have in this video is going to be the area and arc length section of the packet. So I'm going to switch off of me for a second here. Let's see if I can still do this. Okay, so here's where we are on the packet. This lesson might be a little bit longer. To be honest, it probably would have been the equivalent of maybe a day of Bros this week with an altered schedule plus a little bit into the next day. So if it takes you, let's say, 1.5 to 2 days to complete, not a huge deal. That's including that suggested practice problems. But what we're going to mainly talk about in this lesson is area of a sector and arc length and the formulas that are involved with those. Once we're done with that, there's some additional practice at the end that actually is not posted on the website. It should be included in your packet. But we'll go ahead and take a look at some of those as well. So what are we talking about here? Area of a sector is just the area of this piece of the pie right here. And you probably developed some of these formulas back in geometry. But what I'll tell you is that we're going to develop them from the specific perspective of having angle theta in radians. Same thing when we get to arc length. We're going to talk about arc length in radians. So in this example here, to find the area of that sector, well, we can actually set up a proportion and say that the area of the sector that I'm looking for, the shaded region, I'll call that capital A, is to the entire area of the circle, pi r squared. That would equal the ratio of the central angle theta on the inside of our sector as compared to the total number of radians in the circle, which hopefully remember is 2 pi. So what I'm trying to do is figure out, well, what is A? What is the area of the sector in general? So if we cross multiply, we get A times 2 pi equals pi r squared times theta. And then just a quickly dividing both sides by 2 pi here is going to get us to the formula that we're going to use. So if I cross off those 2 pi's, on this side, you'll notice pi cancels top bottom. And we still have that 2 down there. So I'm going to write that just out front as a 1/2 r squared theta. So this is the formula that we're going to use to find the area of a sector. It's 1/2 the radius squared times angle theta, where theta, and this is written in your notes too, theta must be in radians. It wouldn't make sense to plug in a number of degrees for theta because we compared theta in our derivation to 2 pi. So are there formulas that we could use for degrees? Yes, you probably did that in geometry. But we're going to stick with radians since we're pretty comfortable and I hope confident with radians by now being in pre-calc. Okay, so number 1, find the area of a sector whose diameter is 12 and it's intercepted by a central angle of pi over 3. So you don't have to draw a picture for every single example. I'll try and draw one just for this first one so we get some context. If we're thinking about pi over 3 is, I guess if we think of a degree world for a second, it should be 60 degrees, right? So if I start with the center, and if a quarter of a circle would be a central angle of 90, we don't quite want that. We get that central angle there is pi over 3. And our goal is to find the area of the shaded region here. Now, it did tell us that the diameter is 12. So if the diameter is 12, we're going to make a quick jump to say that the radius, therefore, is 6. And if we have the radius is 6, we can then say the area is 1/2 the radius squared times theta, where, hey, luckily, theta is already an angle in radians. So if I simplify this, we're going to get half of 36 times pi over 3. And if I do this correctly, the 2 and the 3 down here would multiply to 6. 6 goes into 36 6 times. So I'm going to actually just leave it as an exact answer. I guess we'd want to look for rounding directions. Sometimes it will say round to the tenths or hundredths, but otherwise we leave it exact. And if we're finding area, this was centimeters up here, so we'll say it's that many centimeters squared. Okay. For these other examples, I may not wind up drawing that diagram. However, if the diagram helps you, go for it. Next one, find the area of a sector with the central angle of 75 degrees and the radius is 7. So it's really tempting sometimes to take that central angle and just sub it right in for theta in the formula. But we do just have to take note that the formula is developed in radians. Okay. So we're going to have to do a quick conversion here, multiply by pi over 180. And in that case, I should probably double check this. I think it's 5 pi over 12 if you reduce it, but you know what? I will double check real quick. So we get 75 over 180, math frac that to get 5/12. Okay, shouldn't have doubted myself the whole time there. Okay, so now that I have it in radians, it's a pretty easy question. The area is 1/2 the radius squared, radius is 7, times central angle in radians, 5 pi over 12. So the one thing I'll say is that if it said exact, you pretty much type in everything on the you see right here except for the pi. So on the calculator, you might do something like 0.5 parentheses. Sorry if this is kind of tough to see on the screen here. Let's see if I don't know if that light really helped. We'll see. But if I do 0.5 times 7 squared and then times 5/12, that's this decimal here. But if I math frac that, oops, I wasn't looking at the calculator. Hold on. All right. Math frac is what I wanted to do. 245/24 pi is what the answer would be in an exact form. So, I mean, that's not the nicest looking answer, but it is exact. Pi, and that would be, what do we have in the radius here? Inches squared. Okay, which is approximately, if you then multiply that by pi, you can say the area of that sector is about 32 square inches. Okay, so depending on where it says to round or what it says in the directions, if I don't give you any directions, the implication would be that we're going to keep this in an exact form. Okay, all right, going on to number 3. We have the area of a sector intercepted by a central angle is 4 pi over 7. And we already know that the area is 16 pi. So find the length of the radius. And without any rounding directions, we'll see what happens in the end. See if I can just move this a little bit. Okay. So given the area, that's going to get plugged in on the left side. 16 pi is the area. That would equal 1/2 of r squared. We don't know the radius. Okay. But we do know the angle theta is 4 pi over 7. Probably a couple different strategies here of how you want to simplify this, but you can take the 1/2 and the 4 pi over 7 and multiply those, right? Commutative property of multiplication there. So that would just become, in this case, let's see, 2 goes into 4 twice, right? I can actually do a little cross canceling there. So that would be 2 pi over 7 now times r squared. And then to get rid of the 2 pi over 7 being multiplied by r squared, I think a lot of us would default to say, hey, just divide by that. But I think it would actually be easier to multiply by the reciprocal. So if you multiply by 7 over 2 pi, well, then those cancel, right? Do the same thing on this side, multiply by 7 over 2 pi. The pi's will go away for sure. 2 goes into 16 8 times, and without even needing the calculator, if you know what 7 times 8 is, we get r squared is 56. Square root, square root. So r is the square root of 56. No shame in not knowing 7 times 8, by the way. I distinctly remember getting that wrong in 4th grade. And my 4th grade teacher who didn't like me made me write my whole times tables all over again just for getting that one wrong. It was a big issue, guys. But listen, now I'm a math teacher. I'm pretty good with 7 times 8. Okay, didn't say to simplify the radical, which actually that can't be so, no, I guess it could be simplified, right? Because if it has an 8 that goes in. But to be honest, not our major concern right now. Unless it had said simplest radical form, then I do something more about that. Okay, so we got a little bit of area of a sector in there. If we go to the next page, we're going to now talk about what if I don't want the area of that sector, but I want the length of the arc on the outside. So I get the impression, without remembering exactly, that I probably called this L in the notes for length. But I would say that in certain, let's say, textbooks or other resources, you might see that that's labeled as S for arc length. To be honest, I don't exactly know why we call it S, but I think L kind of makes sense if I'm talking about a length here. The length of that arc is actually still going to be dependent on the central angle theta there. So you can set up a really similar ratio like we did for the area derivation, that if I take the length over the total length of the circle, which is circumference, right? Circumference, let's see, cherry pie is delicious, yeah, circumference pi d, apple pies R2, areas pi r squared. That might be ringing a bell, but anyway, cherry pie is delicious. I actually like, instead of using pi d, I kind of like 2 pi r just as a default. You'll see why I like 2 pi r in just a second here. So that would equal the ratio of the central angle theta to the entire number of radians in the circle, 2 pi. And then if I cross multiply, I get L times 2 pi equals 2 pi r times theta. Just like we did before, if I want to figure out what is that length, L, we're going to divide both sides by the 2 pi. So the length is, look how nice this works out. The 2 pi's cancel completely top to bottom on the other side as well. So the arc length around the outside for a portion of the circle is just the radius times the measure of that central angle theta. So you can see why I kind of wanted 2 pi r up here, because then you get that nice 2 pi to cancel out over there. So L equals r theta is going to be the formula that we use. And then again, theta must be in radians. Okay, don't plug in any degrees there. It's not going to make any sense. Okay, find the length of an arc whose diameter is 12 and intercepted by a central angle of pi over 3. Sounds familiar. We did this question a second ago as it related to area, right? Find an area, diameter 12, central angle pi over 3. But again, the main idea now is I don't want that shaded region. I want what's the distance from there to there. So that's what we're doing in this next question. Okay, the length would be the radius times theta. Okay, so the radius would be 6. The angle's pi over 3. All right, so 3 goes into 6 twice, so the length should be 2 pi. And since this is a linear distance, we would say that this is just 2 pi centimeters, not square centimeters. We're not calculating area anymore. That's a pretty quick sub in to get the length as 2 pi. So you can probably do something similar if the central angle is given to us in degrees, right? So the radius in this case is 18, central angle is 20. So just make sure that you take that 20 and convert it into radians first by multiplying by pi over 180. This would reduce to pi over 9 is what we're going to get there. So if I have that's my angle, the length would be the radius of 18 times pi over 9. And this is just coincidence that the length in this case comes out to be 2 pi again. So it would be 2 pi inches this time. The length is not always 2 pi, just happened to be coincidental. A fantastic application of this idea is the idea of finding the distance between two cities. This might be groundbreaking information, but the world, the Earth, is round. Did you know that, Elodie? That the Earth is round?
I knew that it's a sphere and it keeps spinning so slow. But
How did you know that?
I just learned from science in my old school.
In your old school?
Yeah, I learned from science in my old school. Remember
Aw.
that field trip I went when I went to the museum?
Yes, you went to the planetarium and they taught you that there?
Yeah, they taught me that it spins around.
Okay, so guys, listen, not only does Elodie know that the Earth is round, she knows it's a sphere because she knows three-dimensional shapes, and she knows that it's spinning really slowly because she went to the planetarium on a field trip at one point. So thanks for chiming in there, Elodie. I'm going to do this question now with my students.
Yeah,
Okay.
but I want to send this in the mail.
Okay, we'll send that in the mail later. Okay, I'll check back in with you.
After that, because
Yeah.
I don't want to rush in.
Okay, sounds like a plan. All right, so how do we find the distance between these two cities? Given the radius of the Earth is approximately 6,400 kilometers, approximate the following distances. So I can figure out if two cities are on the same line of longitude. First of all, actually, that's kind of an important piece. So these cities that I'm picking are approximately on the same line of longitude, but on different lines of latitude. How can I find the distance between them? So here's kind of what I want you to think about for A. I'll draw pictures for both of these. So we've got my round Earth right here. And what I know is that the equator is at 0 degrees north. Okay. So we've got Charleston, South Carolina. That's at 33 degrees north. So that would be 33 degrees north of the equator. So I'm going to say that, let's say that that's about here. So I'm going to put South Carolina right there. And then if Toronto, Ontario is at 43 degrees north, that would be maybe right about here. We'll call this Ontario. So those 33 and 43 are drawn respectively from the angle of 0. That's right where the equator would lie. So what I want to know is what's the distance between those two cities? And oh yeah, since the Earth is a sphere and round along the outside, that's going to be an application of arc length. So the length would just be the radius times theta. The radius we decided, we're given that that's 6,400 kilometers. And then I just have to know what's the measure of that central angle. Well, if I know that to the bottom where South Carolina is 33, whole thing is 43. Do you know what 43 minus 33 is, Elodie? That might be a tough one for kindergarten. What's 5 plus 5?
10.
10, we got it. Okay, 10 degrees is what's left. So if we've got 10 in there, just make sure when you plug it in, I know how tempting it is, but we've got to plug it in as 10 pi over 180. Got to convert to radians. Okay. So what you're going to do is you're going to type this in the calculator because it wouldn't make sense that the distance, sorry, it's not that it wouldn't make sense. It's not going to mean a lot to somebody if you say, hey, the distance from Charleston to Toronto is this many pi kilometers. We probably wouldn't put it in terms of pi because people don't necessarily think in those terms. Maybe math teachers do, but most people out in the world wouldn't know what you were talking about. Okay, but if I type that in, here's what I got as an answer. Sorry if that's a little tough to see, but I got 1,117 kilometers. And I'll tell you the rounding standard for questions like this, and you'll see this, I believe, in the textbook as well, is to round to the nearest 100. 100. So we're going to round to the hundreds place. Now, notice that that's not the hundredths place. Because when we're talking about such a large distance, we don't necessarily care about, in this case, the 17 extra kilometers. If you say that the length or the distance between those cities is approximately 1,100 kilometers, you know, that last 17 kilometers is pretty negligible there, right? Wouldn't really be a big difference in terms of the grand scheme of how far apart those two cities are. So you'll see that round to the nearest 100 direction, which is not somewhere where we typically round, but you know the hundreds place, right?
Yeah, I was going to tell you I know the 100th place.
That's awesome. Yes, they're learning about hundreds place in kindergarten right now. So yeah. It's cool stuff. Because I think today is day 115 of school, maybe?
No, not 15. I think.
Because I think yesterday was day 114. But I don't know.
No, Today's the 106th.
Oh, maybe we missed a day. 116. Okay, sounds good. All right, so this last one, it's a really similar application, guys. The only reason I want to do it is just to address that, in this case, we have one city that's 45 degrees north, the other's 34 degrees south of the equator. So the 45 degrees north might be here for Nova Scotia, but for 34 degrees south, just make sure you go below the equator here in our case. So it's going to be something that looks like this to where we are for Argentina. So when I do my arc length here, it's still the radius of the Earth doesn't change. That's still 6,400. But the angle that I need, what did I do here? I subtracted those to get the angle of 10 degrees. Well, in this case, I'm hoping you're thinking if this is 45 and this is 34, we're definitely going to have to add those together to get the angle that's required. So that's going to be a total of 79. Okay, multiplied by pi over 180 when you plug that in. So that distance is actually going to be quite a bit larger than the distance from, where were we, Charleston and Toronto there. So the distance that I'm getting here is 8,800 kilometers. And you guys can type that in the calculator and confirm that for me, but approximately this many kilometers. And again, I'm rounding to that hundredths place right here. So hopefully you guys can follow that rounding standard in the suggested practice. Okay, we actually have two more formulas to learn today. We had one about area of a sector, one about arc length. Last two formulas are both related to the area of a triangle. And you might think you know the area of a triangle because you learn it in, I don't know, I think I have 4th grade up here. Is that what I said in the notes? Yes, we know from 4th grade. And the reason why I say 4th grade is that there used to be that show, Are You Smarter Than a 5th Grader? I don't think it's on anymore. But there was a question once in the 4th grade math category that said, what's the formula for the area of a triangle? I'm like, holy cow, they know that in 4th grade? But anyway, here's the pre-calc trig version of area of a triangle. 1/2 base times height is great and all, but if you don't necessarily know the length of the base and the length of the height of a triangle, there is an alternative formula we can use with a little bit of trig knowledge. So if you go from angle A right here, it says sine of A is equal to opposite over hypotenuse. So that would be the height over side B. With some quick rearranging, you get that the height equals B sine A. So if you come to your formula, the height's going to get replaced with B sine A. And if you look at the base of the triangle right now, the base of the triangle is labeled as C because it's across from angle C here. So if you replace C where the base is, and you replace B sine A where the height is, you get this new formula 1/2 BC sine A. So the advantage to having this is that if you look at where B and C are located, those are two sides of the triangle. So maybe those would be easier to measure in a real world context than knowing what the height and the base are. And then if we had some tool to measure the angle here, we can calculate the area. There is a good note over here that I'd want you to pay attention to, is that in order to use this formula, you need to have side angle side. Just like for law of cosines, you need the two sides that make up the angle that you know the measure of in order to plug them into this area formula. And you don't have to have a triangle ABC. It could be really any given information. This example is actually pretty straightforward. It gives you two sides in a triangle, and we know that the angle between those two sides is 47 degrees. What's the area of the triangle? This formula was not dependent on angle A being in radians, so you don't need radians at all here. You're just going to say that the area is 1/2 the product of the two sides, 28 and 35. And at the end, sine of the angle between those two sides, which is 47. Okay, so if I come over here, we've got 0.5 times 28 times 35. And then sine 47 at the end. Make sure you're in degree mode. I got 358.3. And again, not really any rounding directions here. I'll go to the nearest square inch. So we'll say this is 358 inches squared. Okay. And that's the only example I have using this formula here, guys. It is pretty user-friendly as long as you have that side angle side set up. You'll see some examples that you can practice with. And in fact, maybe we'll do one more with it on the other practice section. Down here, we have one last formula. It's what if I don't have side angle side, but I have side, side, side? Well, you actually have two options. One option would be if you have side, 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 maybe that's standing out to you as a law of cosines case, which it is. So you can find an angle in the triangle, actually any angle, and then use this formula right here. Because if you have two sides and the angle in between, you'd be good to go. But as an alternative, there is a formula in the book called Heron's formula. And Heron's formula is if you have side, 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 it winds up being, and there's a derivation for this in the textbook, I believe. It's the square root of s times s minus a times s minus b and s minus c. Okay, a, b, and c are the side lengths of the triangle. So what is this value s? S is called the semi-perimeter of the triangle. So I'll tell you in general, S is, if it's a semi-perimeter, well, perimeter would be the sum of the sides. Semi would be, well, take that and cut it in half. It's half the perimeter. So also, once we know that, pretty easy to apply. If these are the three sides of a triangular lot, what is the area of the lot? So the first thing I might do is calculate the semi-perimeter. So that's 42.5 plus 37 plus 28.5, all divided by 2. Okay. So if I do that quick off to the side here, it looks like the semi-perimeter is 54. Okay. And knowing the semi-perimeter is 54, I'll then plug that in to Heron's formula, which says take the square root of S, which is 54, times S minus A. It doesn't really matter which one's ABC, right? It's 54 minus the first side, 54 minus the second side, 54 minus the third side, if you can squeeze that all in here. And that's going to be our approximate area. Okay, so it's the square root of 54 times 54 minus 42.5. Just type it in as is. Don't even worry about doing any of the subtraction in your head. Who wants to do that? Not me. All right, I'm getting 519. Didn't give us any units here, did it? Oh, meters. Yeah, there we go. All right, so it's that many meters squared. So just a quick alternative to finding area. This way, it's probably a little bit faster to do this than, let's say, what I suggested earlier, which was law of cosines to find an angle, and then use the formula 1/2 AB sine C or BC sine A, whatever I wrote up there. Okay, so that's really actually all the new stuff for today. There is some other practice here, and I may not do all of this. Maybe I'll just do quickly talk about 1 and 3. Actually, if I'm being honest, I think 2 is a homework question. So you might see that come up in the suggested practice that I recommended for you. But in the other area of practice, I actually do want to talk about number 1 because it's going to involve a couple formulas that we've seen today.
I just want to ask you one
What do you
thing.
want to ask?
At the end, I'm going to say, have a good day.
Okay, we can do that at the end. Okay. All right, so find the exact area of the segment below. So what is a segment? First of all, it's kind of odd to think of something as being a segment. But this region right here that's shaded in, that's what's considered to be a segment of a circle. Okay, so that's the area that we're looking for. So in order to do that, there's going to be actually 2 things that we're going to figure out. If you find the area of the entire sector, remember that's the whole piece of the pie, the whole thing shaded in, and then you subtract the area of the triangle right here, that's going to leave you left over with this shaded segment area. So again, piece of the pie, whole thing, minus that unshaded triangle gives you what's left down here shaded in. So the area of the sector, as a reminder, that was the 1/2 r squared theta formula. Formula for area of a triangle, well, I'm pretty sure we have side angle side, right? If this is a radius, this is a radius. So if you have side angle side, you can do 1/2. I'll do, I think we wrote it in the notes as BC sine A, something like that. Okay. So if we actually just plug in what we know, it's 1/2 of 6 squared. Theta in this case is pi over 6. So we'll plug that in there. Remember, theta must be in radians to do this. Then over here, minus 1/2 6 times 6, sine of the angle in between, which is pi over 6. All right, you just gotta be a little bit cautious about this because if you're gonna type this in the calculator, this would then have to be in radian mode. You're gonna do sine of a radian angle. I'm convinced we actually don't need the calculator because, let's see, remember 6 squared is 36. Okay, So if you have down here 12, 2 times 6 is 12, that goes into 36 3 times. So that part's 3 pi in an exact form. So what is all of this? Okay, ready for that? Sine of pi over 6. Why don't we need a calculator? Because it's actually a nice reference angle. Pi over 6, I'm hoping you're thinking that's 30, right? So if that's 30, you get 1 radical 3, 2 for the sides. So then sine of pi over 6 is opposite of right hypotenuse, 1/2. So this thing right here, if that part of it's 1/2, you're doing half of 36 and then taking half of that again, right? So I guess all in all, that sounds like we're going to be left with 9. So the exact area is 3 pi minus 9, and this would just be square units. Okay, or if you wanted to round it so you can kind of visualize what that is as a decimal in square units, 3 pi minus 9 is about 0.42. It's a small little area there. So to the nearest hundredth, 0.42 square units there. So if you're going to type that into the calculator, again, since we have sine of a radian angle, you would have to switch this over to radian mode. So just be careful about that. This angle has to get plugged in as radians here. This one, it doesn't really need radians. If you plugged in 30 degrees here and left it in degree mode, you could actually type in this whole thing. Okay, so even though this is a radian angle, you don't need radian mode to type that in. And that's actually kind of a common misconception that students have. It's only when you're doing sine, cos, tan, or some trig of a radian angle that you need to be in radian mode. Okay, so again, this is in the suggested practice, so maybe take a look at that. The answers should actually be on the website anyway. And the last one, number 3, find the area of a parallel. Oh no, the parallelogram's back again. You know what a parallelogram is, Elodie?
No.
You haven't learned that yet? It's the shape right here.
Oh yeah, I learned that shape at school, and we also have it at home. I can show you an example.
All right, why don't you go look for it while I'm finishing up this example. All right, so find the area given that the sides are, wow, long parallelogram here. We have 12 miles and 15 miles for the lengths. And it says it has one angle measuring 52 degrees. Okay, so I'm hoping what you would think here is, we did a parallelogram the other day because we had to find the length of a diagonal, right? And that was an application, I believe, of law of cosines because we have side angle side. Oh, but yeah, side angle side is also what we need to find the area. So if you actually just think about splitting this into 2 triangles, these 2 triangles have equal areas. Their dimensions would be the same. This would be 15, this would be 12, this angle's 52 according to parallelogram properties. So what you can do is you can actually just take the area of one triangle and double it. So if the area is 1/2, this side 12 times 15 times sine of 52, I'm going to take whatever that is and double it. All right, so let's check out what that is. 0.5 times 12 times 15 sine 52. So the area of just one triangle is about 70.92. Double that to get 141.84. So I don't know if it says anything about rounding here. I'll go just for fun to the 100th place. You found it? Oh, good, because I actually just finished. 141.84 square miles. Very large parallelogram. I actually usually get the natural question, Mr. All, do we have to put the 1/2 in there if we're just going to double it anyway? The answer is no, you don't have to. So parallelogram's area would just be AB sine C. Man, this would have really helped me to draw a nice parallelogram. This is what Elodie found. We have a little game that has some different shapes and stuff like that. And that is exactly a parallelogram, actually, right? If I turn it this way, this way maybe. Nope. Okay. Anyway, so we have a nice, I could have used this as a scale model for us here. Okay, perfect. So Elodie, you wanted to say goodbye to the class right before I turn this off here, right?
Yeah.
All right, let me see if we can switch this back over so we can see you. Oh, there you are. So what do you want to say?
Have a great day, and thank you for watching this show. Goodbye.
Oh, that was such a great ending, guys. Listen, there's not going to be a better video than this one. So keep watching this on repeat. Hopefully all is well by you. I'll be talking to you soon. Take care. One more video to go in this unit.